Okay, hello again. So in this session, I'm going to derive the differential form of momentum equation in the inviscid form, which is called Euler equation. Okay. So again, we are going to start with the integral form of the equation, and then using the Gauss's theorem, we are going to convert all the surface integrals to volume integrals and then derive the differential form of the momentum equation. So first, we get started by writing the integral form of the momentum equation. Momentum conservation equation. So we have done it before. So we are gonna I'm just gonna copy that. So this is the whole thing is the integral form of the momentum equation. So let's just copy it. So this is the right hand side, and then the left hand side I'm just gonna write it down. So it's partial over partial t partial over partial t of integral of rho v dv plus integral n dot rho v over the surface dA. So the second one is the integral over the surface equals to the right hand side, which is the sum of the forces. Okay. So now this is the integral form of the momentum equation, and we assume, or you can consider, inviscid flow. We consider an inviscid flows where F viscosity is 0. So for inviscid flows, that means we don't have any viscosity. So F viscosity should be 0. And we also assume that we have no external forces acting on the fluid. Okay. So this means that these two terms are just going to cancel out. So this one is also because we are in the inviscid case. We are only investigating the inviscid case, where we don't have any viscosity. Okay. So now using these assumptions, we use Gauss's theorem to change area integrals okay. Okay, so using this Gauss's theorem to change the area integrals, what we get is as follows. First, again, like the continuity equation, I can take this into the integral, okay, because dv is fixed, so the only thing that is changing here is this term. So what I'm gonna get is as follows. The first term is this integral over the control volume of partial over partial t of rho v and then the second thing, I'm going to use this for this one. I'm going to use the Gauss's theorem. So for Gauss theorem, only for the mass, we got this. If you just put it for the mass, you will get this, right? But now we have momentum, so it's going to be a little bit different. So we'll have an additional term here. So it's going to be as the first one is the divergence of rho v with v, because we have more terms here. Okay, and then we have another term which is going to be rho v divergence dot grad times v. Okay, so this is, you can get it from Gauss's theorem. I'm not going to go through that. If you use Gauss's theorem for this term, you are gonna get these two here. Okay, I'm not gonna prove that, but this is what you are gonna get, and this is the integral over the control volume. So over volume dv, and then this equals to what? So let's see, we got it, we had it before, so let me just write it down. What is np dA when you get the integral? So here we have it. So it's gonna be this np dA, the integral over the control surface. If we want to take it to convert it to this area integral to the volume integral, what we are gonna get is this. So it's the integral minus integral of grad p dVA. Okay, so let me just modify this a little bit. So we are going to have on the right hand side the integral of minus grad p, and then what is the second term? We have the second term is the body force or the weight of the fluid, which is going to be rho g, and then the whole thing is the integral over the control volume or dV. And then we assume that we don't have viscous forces, so it's inviscid, and also we don't have any external forces, so we just neglect those forces. So if we rearrange the terms here, we are going to get the integral over the control volume, right, the whole control volume of partial over partial t of rho v plus grad dot rho v times v plus rho v dot grad v plus, I take these to the left hand side, grad p minus rho g dv equals to 0. Okay. So again, similar to the continuity equation, since CV is arbitrary, the integrand itself must be 0, because this equality is valid for any arbitrary CV. So the only way it can be valid is that the integrand itself is 0. So what does this mean? This gives me this equation, partial over partial t of rho v plus grad dot rho v v plus rho v dot grad v plus grad p minus rho g equals to 0. So I can write the first term, rho v, partial rho v over partial t, using the differentiation rule to rho partial v partial t plus v partial rho over partial t. Okay, and now I can rearrange the terms as follows. So I can write the original equation as v partial rho over partial t plus, for this term, I'm going to write it as follows. For this term, this is a scalar which is multiplied by a vector. So I can just take the vector here and write the scalar on the right hand side, on the right side of that. So it's going to be v grad dot rho v plus, and then we have this term. So the first term was this. Now the second term of this is here, so I'm just going to write it down. Rho partial v over partial t plus the second term we have rho, I can take it out, v dot grad times v equals to minus grad p plus rho g, which are the forces. Okay. So let's see what we have here. So these two terms, what they are. So we have v, let's factor v. So we are gonna have partial rho over partial t plus divergence of rho v, okay? And for these two terms, I can factor out rho, so I am going to have partial v over partial t plus v dot grad v. Okay. So let's see what is this. Does this look familiar to you? Yeah. What do you think? This is continuity equation. Look at it. It's exactly continuity equation on the left-hand side, right? So that means that this is zero because of continuity, because of mass continuity conservation, mass conservation. So this term is zero because it's exactly continuity equation. Okay. How about this term? What does this remind you? Let's go back again to the material derivative. Here. It looks like this, right? So it's just sum of the Eulerian and convective acceleration, which is what? Which is going to equal to the Lagrangian acceleration or material derivative of v. So it's just dv over dt. So finally, the final equation, the differential equation that we get is as this: rho dv over dt equals to minus grad p plus rho g. Okay. This is a very important equation. This equation is the momentum equation in differential force for inviscid flows, or we also call this Euler's equation or momentum equation in differential form for inviscid flows. Okay, so if we have viscosity, we will have one more term here, and also if we have external forces, we will have other forces on the right hand side. And so if you have viscosity, then the equation is for viscous flows, and we are going to derive that later in the course. It's a little bit harder to get the viscous. We want to get the viscous force in terms also of the in terms of the velocity, and so for that, that is called what we call it Navier Stokes equation. Okay, which is the momentum equation in differential form for viscous flows, okay, for any general flows. It's called Navier-Stokes equation. It's a little bit more complicated than this this equation, which is Euler's equation, which we don't have any viscosity here. Okay, so that's it for this lecture. So let me briefly overview and review what we did in this lecture. So first of all, we defined the divergence theorem. Just refresh your minds, that is used for converting the surface integrals or area integrals to volume integrals. Okay, so this is the whole thing about the whole theorem of the divergence theorem or the Gauss's theorem, which, as you see, changes the surface integral to a volume integral. Okay, so I wrote it also for the mass, and this is what you get for that. And similarly, you can show it for changing the area integrals. For example, for pressure, it's going to be something like this. Okay, so I didn't prove this, but these are some mathematical identities that you can show and prove. And then we use that to convert the continuity equation, to derive the continuity equation in differential form by converting the integral form of continuity into its differential form. So we get this, and then because this is valid in any controlled volume, so we finally got this form of continuity equation. So this is, we also rearranged the terms, and this was another form of the continuity equation that we got. And then we define incompressible flows, which is defined as this: when the divergence of the velocity or grad dot v equals to 0, that is the definition of compressible flows. And rho constant is just a spatial case of incompressible flows. But rho may change spatially, but the flow could be incompressible still. Again, if these the other terms kind of cancel this d rho over dt equals to 0. So this is what really we care, is d rho over dt should be 0 to define the incompressible flows. Then we briefly talked about Einstein's index notation, which is, I think, a useful thing for you to learn, especially for differential equations. And then we derive the differential form of momentum equation, or Euler's equation. So we started with the integral form of the momentum equation. We consider inviscid flows and also no external forces. And then again use the Gauss's theorem to change area integrals into volume integrals. So we changed everything and we got to this equation. And again, because this is valid in any CV, which is any arbitrary CV, so the integrand itself must be 0. So we just rearranged the terms and we found that some of the terms are actually, we can get the continuity out of this equation because also it's equals to zero. It equals to zero. So what we finally got is this equation that is shown here, which is the Euler's equation or the momentum equation in differential form for inviscid flow. So in the future lectures, I'm going to also add the viscosity term here to get a more general equation for the momentum equation, differential form of momentum equation, which is called Navier-Stokes equation. That's a very important equation in fluid mechanics because we use that a lot for actually solving fluid flows in numerical analysis and numerical programs, for example, CFD codes or computational fluid dynamics codes. That's the basis of all these models. So this one, which is the Navier-Stokes equation, and also continuity equation that we covered before that. Thank you very much, everyone.